All right, so today I was hoping to basically give you a background on some of the different systems that we make at SonTek, and I'll be showing you different data examples, especially during some flooding events. And then I wanted to touch base on some collaborative research that we've been doing with Professor Marian Muste from University of Iowa, as well as Dr. Dongsu Kim from KIST in Korea. So all of the plots and sort of results and analyses will be the result of studies from Marian and Dongsu today. All right, so for those of you who aren't familiar with SonTek, we were founded in 1992 in San Diego, California, and we are the manufacturer of acoustic Doppler current meters. So our products measure water speed and direction in various environments, ranging from rivers to streams, to pipes, all the way to oceans and everything in between. So on the bottom here, you can see a photo of the people who work at our San Diego facility to make our systems. And on the right, I have pictured a range of our different systems that we manufacture. So you'll see that they come in different shapes and sizes, and those things correspond to different applications that we make them for. So on top here, you'll see the IQ and SL series. In today's talk, I'll be really focusing on the SL series here. These are our continuous monitoring devices, and I'll explain what that means in a little bit. And then you have the well-known flow tracker device, as well as the newer RS5 ADCP, and our big brother to that, our M9 and S5 series. All right, so let's talk about monitoring flow, especially during a flood event. Throughout this conference, we've heard a lot about the traditional stage-discharge relationship. On Tuesday, if you're on the field trip, Sean was showing us his gaging station, which uses the stage-discharge relationship, and we've heard from Brian here on some of the complications that you might experience from stage-discharge relationships. So we'll touch base on that briefly, but the meat of the talk, I really wanted to discuss a different method, index velocity rating, which is, it's used frequently, but definitely not nearly as frequently as a traditional stage-discharge relationship. So I'll be showing some examples of this, why you might want to use an index velocity rating, and some more complex situations that will arise, especially during flooding events. All right, so we don't need to discuss too much on the theory behind stage-discharge relationships, so please bear with me as I kind of skim through Hydrology 101 here. In a stage-discharge relationship, we make certain assumptions about the flow. So the first thing is we assume that we have steady flow, so that means constant in time. And then we assume uniform flow, which means constant in space. So most of the time when we make these assumptions, we're looking at sites that look like this bottom left site here. So straight, steady flow, concrete lined canal here. Unfortunately, most of the time, we are actually experiencing sites that look more like the one on the right. All right, so as I mentioned before, the stage-discharge relationships are the most widely used discharge method, especially in the US at gaging sites. It is the cheapest, simplest to install and maintain, and it requires the least amount of data processing afterwards. So with your stage-discharge relationship, as we all know, we require some sort of continuous stage measurement at your site, and then we go through and we make these instantaneous discharge measurements. And so we want to be able to cover a wide range of discharges and develop your rating between your stage and your discharge. So pictured here, what I mean by instantaneous discharge measurement is that you physically go to a site, you have your instrument, you make the measurement, and that value of discharge is just a snapshot in time, the instantaneous discharge at that given time. All right, so what happens when some of our assumptions break down? So some of the complications that you might see at various sites are non-uniform flow. So on the right here, I have pictured a velocity profile from a SonTek side-looking system. So these things are mounted on the side of a stream or a canal, and they point perpendicular to the flow. So this red line represents the downstream or X direction velocity, and the blue line here is a Y or cross-stream velocity. So when you move down the plot, you're moving further away from the instrument. And so you'll see that as you travel further away from the instrument, we have an increase in the x component of velocity. So as we're traveling away towards the opposite bank, there's actually an increase or an acceleration of the velocity as we move. And so this being a concrete line canal, we don't necessarily expect complex or non-uniform flow like this. So this is, I thought it was quite illustrative of actually putting in a velocity measurement and really learning about your more complex flows when you don't really necessarily expect this. So other complications that you might see at sites, you've got backwater eddies, flashy events like flooding, vegetation, tributaries, things that are adding or subtracting water into different locations, dams or other structures, that sort of thing. So as you're thinking about your own gaging sites, you're probably thinking, well, most of my sites have at least one, if not multiple, issues or complications that I've listed here. So let's take a step back and just look at some data. So this data comes from a site in Florida, and I'll be showing you data from the Hurricane Irma event in September 2017. And so this was a hurricane that hit Florida, a Category 5 hurricane with maximum winds of 185 miles per hour. So unfortunately, 134 lives were lost in this event, and the whole area just experienced massive flooding. So we'll be looking at data from this gaging station, which is located in Kissimmee, Florida. And this one was actually, it drew quite a bit of attention because it was the closest gaging station to the Good Samaritan retirement community. And this was a community where many of the officials were really paying attention to because it was quite difficult to evacuate the residents and save the homes in this area. So on the left here we have, again, the gaging station, and on the right this is the picture after Hurricane Irma came through. So you'll notice the water levels is up to the catwalk there already. All right, so in terms of an instantaneous discharge measurement, this data came from an M9, River Surveyor M9 system. So on the left we have your typical transect that was made before the hurricane. And so I know no one can read these numbers here, but the extent of the depth was about 8 feet at the deepest part of the channel, and then we were able to make about maybe 70 feet across the channel before we hit the banks here. So this is just what a typical velocity contour profile looks like. This is an interesting profile because you're seeing these two pulses of warmer colored contours, which represent higher velocities. So these kind of correspond to the deeper parts of the channel here. And let's look at the right side, which is after the hurricane came through. The extent of the depth has increased dramatically. Now we're at almost 14 feet deep compared to the 8 feet from before. And horizontally, we've gone almost 120 feet across. All right, so on these edges here, we're actually measuring the floodplain, all the water that has overspilled the bank. So just an example of some of the data that you can collect during a flood. All right, so at this gaging station, there was also a side looker. And the data here, this top plot, this red line shows the x velocities, so downstream velocities again. And then the blue line represents the cross-stream velocities. And then you can see the stage actually in the black line behind there. So this is before the hurricane, and then you see the big peak in the flows, in the velocities as we go. And what's interesting here is that we see the big spike in velocity, and then you can kind of see this sloshing back and forth as the water is coming through in these pulses almost. And on top of this, normally when we measure, we expect these y velocities to be very close to zero because our instrument is pointing perpendicular to the flow. So what happens here is that the hurricane comes through, the flood comes through, and we start seeing an increase in the y velocities as the water is being pushed over the banks. So this is just kind of an interesting way to visualize what is actually physically happening with the water during a flood event. All right, so I mentioned our instantaneous measurement systems. On the other side, we have our continuous monitoring systems. So these are the systems where you set them up in the field, install them, and then let them run as they're collecting data. Right. So we want to basically capture these more complex flooding events using both the instantaneous and continuous systems. And this method is referred to as velocity indexing. And the idea behind developing an index rating at a site is basically to take your instantaneous discharge measurement and develop a relationship between your instantaneous discharge or your mean velocities that you measure versus the measured discharge, the measured velocity of your continuous system. So in this way, you always have a measurement of your velocity in your stream, and you relate that to your actual discharge measurements. And you also develop a relationship between the area and the stage. So already you can see that the parameters are building here. There are many more parameters that you have to measure compared to a normal stage discharge relationship. The processing is more involved. It takes a longer time to achieve a proper rating over a larger range of discharges that you're interested in. But oftentimes this is what's needed, especially at the more complex sites, the sites that experience frequent flooding, that sort of thing. So you'll basically be collecting all these measurements, crunching the data in prescribed spreadsheets or software packages. And in that way, you develop your discharge rating curve. All right, so now I want to get into talking about hysteresis. For those of you who were in the USGS session this morning, you might remember that Frank Engel mentioned these looped ratings that often occur at various sites. So this is what I'm talking about, and this is just hysteresis is a fancy word for the looped ratings. What does hysteresis mean? So let's look at the example of normal ideal flow, which is on the top here. We've got our normal stage discharge relationship, one-to-one relationship between your stage and your discharge. If you plot the peak in your stage and your peak in your discharge over time, you'll see the big peak, and these peaks match up between your stage and your discharge. All right, so what happens during a flooding event, and what does it mean to have hysteresis? Basically, it means that you have these looped ratings where when you go out, you get a different result compared to when you come back in. So the flow has some sort of memory in terms of what's happened before it, and that describes what happens afterwards. So you can see that if you're trying to read off your stage discharge relationship, well, for one stage, you are not going to get a single discharge value. So this really complicates things. When you plot the peak in your stage versus your peak in your discharge versus your peak in your velocities during these events, you'll see that they start to be offset. And often what happens is that your peak in your velocity and your peak in your discharge happen before your peak in your stage. So let's just keep that in mind, and I'll touch base on that in a little bit too. All right, so first some data examples. This is from a study that's currently in progress by Marian here. So this is from a USGS site in the Illinois River in Henry, Illinois. And this is the regression equation that's used at the site. There's actually two of them. This is the equation that relates the measured velocity by a side-looking system to the mean velocity in the channel. So you'll see that this top equation here, I don't know if you can see it, but it actually uses two different variables in a nonlinear relationship. So we're relating the mean velocity to the stage and an index velocity, so that's your measured velocity by your instrument. And then finally, the regression equation that's used presently is actually a little bit more simple. It's just a linear equation that uses only the measured velocity. So you can play around with this and look at your R-squareds and just make sure that you're using the best equation for your site. And that changes over time given whatever situation that you're in. So throughout the years, this site has had a nice time series using the side-looking systems. And so this is just showing the 2017 through 2019 index velocity, so that's measured velocity, in the red line here. And behind that, you see this faint blue line, that's the stage. All right. And so you can see these various peaks. These are all storm events that have occurred at this site. This green dotted line here is the action stage. So once the stage gets above that green line, we start seeing the alerts and the warnings pop up. So you see that not all events are actually above the action stage, and so some of these are just storm pulses. They're not actually flooding events and things you should worry about. So if you plot the stage versus discharge for all of these pulses, all of these events, we start seeing that, at least for this site in particular, almost every single pulse has hysteresis. Almost every single one of these is a looped rating. So throughout the years 2014, 15, all the way to 2019, these hysteresis looped ratings are plotted here. And you'll see that they really vary in terms of their width and their shape and the extent of the discharge. And this really corresponds to the severity of these events, right? And so what Marian Muste and Dongsu are looking into is to use these loops, the shapes of these loops, to develop some sort of a severity index. So knowing this at your site, you might be able to determine, after this event has occurred, what type of severity you're looking at for these events. All right, some more data examples here. This is an example of flooding in Texas that occurred in 2006. And there's an older style side-looking system installed here. And here I'm plotting the velocity in this pink line here. And the blue line behind that is the stage. So you'll notice the peak in the stage occurred here. And if you look at the peak in the velocity, like I mentioned before, we have quite a bit of an offset. So in this particular case, during this event, we actually have about 2.5 days of time between peaks here. So if you imagine you have this velocity information, this velocity being recorded at your site, in this particular case, you had 2.5 days to make management decisions, warning decisions, alerts, that sort of thing. So if you have this information, you know this about your site, this will help you in terms of your early warning systems. So just to reiterate, velocity data will measure your flow directly. You're going to be able to understand certain nuances and more complications in especially a flash flooding event. And it could actually be a valuable or early warning parameter, especially during a flood event. So this is kind of a conceptual model, but once we add in hysteresis into a floodplain model, we actually start getting a different result. So the blue line here outlines the static inundation map. So this is without hysteresis, what we expect to see from a floodplain model. And then this dotted red line is the result of adding the effects of hysteresis into this model. So you'll see that these hysteretic events at specific sites are really contributing to a different result in terms of your early warning systems here. So just to reiterate again, as we're learning more about hysteresis and the frequency of occurrence, especially in certain sites like this one on the Illinois River, we're really starting to learn that velocity measurements in particular may be very critical in terms of helping our early warning systems in this case. And I believe that's all I have for you today. So I'll open it up to questions, and thanks for listening. Mark.
This feels like a silly question to ask, but I'm curious about just the installation of these devices because, ideally they're going to be underwater all the time, right?
Mm-hmm.
And I'm trying to understand how you would install it in both the urban setting along the my channel or even in a natural setting in a way that it is going to be stable, reliable, protect the damage. So do you mind giving a little bit more information about the installation of stuff?
Yeah, sure. That's really always a challenge, right? To really be able to capture the highest peak flows and then the lowest, almost dry conditions. So with the side lookers in particular, you do have to be careful about that, and knowing the range of stages that you have at a certain site is critical for this sort of situation. These systems can be left out to dry and they can detect if they're in water or not. So they go into this low pinging mode once they're out of water. But generally speaking, you want to be in water to be able to measure it. So you really have to be aware of your lowest stage and just for your given site and your application, know what the most important time frame of measurement is for you. We do have the IQs that were pictured at the beginning of the presentation. So those are installed on the bottom of the canal and they look upwards of the channel. So those handle wide ranges and stages. However, they do have limitations in terms of sedimentation and things building up on top. So it's just always a balance depending on what you have at a certain site.
Is it like an ideal place to put it in the channel in terms of how high up, or is it? I mean, I know it's going to be site specific, water specific.
Yeah,
what's the best place?
it really depends, but the important aspect is what we call the aspect ratio. And usually that's about 1 to 20, so that means that for every 1 foot in the vertical, you can go about 20 feet out before you hit either the top or the bottom of the channel. And so that's when you start getting interference from the beams. So that's an important aspect to think about when you're actually thinking about installing one of these systems. No problem. Evan?
Does hysteresis exist in all river systems, or is it more commonly in like a wider channel like the ones that you showed?
To my knowledge, it really depends. And these studies from Dr. Muste, they're really starting to highlight the fact that it might occur more frequently than we think, but it's really site dependent. Yeah.
It's really linked to bed deformation. The more deformation you get in the bed, if you can envision your depth might be, your stage might be staying the same, but you're getting higher velocities and you're deforming the bed and actually moving sediment. So you've actually got more flux through the cross section at the same stage. So it's hard to spot because you'll see the stage come up and it'll just kind of hang out there, but it's actually increasing the discharge.
Mm-hmm.
I think I've seen some, you can maybe see this in the YouTube flume. I think I saw that in the flume one time too.
Oh, okay.
Where they had something that made it easier to conceptualize. So the more mobile the bed is, the more you can see it. So that study, is it ongoing by Muste? Is it still ongoing? That looks really interesting because then you can just look at the shape and that's going to infer everything that's going on.
Absolutely,
So.
yeah.
It's also an artifact of the changing slope as you go through the hydrograph. You pointed out in the
Absolutely.
just the falling around. Think about this. What's the effect of controlling reach length that you're dealing with? And how does that hydraulic slope change over the hydrograph? And whether that's substantial, whether it's substantial loop rating or not, it won't at all.
Yeah.
The trick I found from, I don't remember if it was Bob Holmes or someone else in the USGS, and they plotted out DHDT over the course of a given measurement, and versus whether or not that measurement plots right or left or on a given rating curve.
Huh.
The tighter that is, you have essentially no effect. But
Yeah.
the more we look at it, you see that, a larger percent difference as you look at changing the stage of the measurement.
Interesting. I'm glad you brought up the slope aspect because that's something I didn't describe as a slope area method, which is another method that we're actually looking at in terms of how well does it capture the hysteresis. And it seems like it's doing a really good job, actually. Yeah.
For the side lookers, it sounds like, so my question is how far out can they see? But it sounds like it's going to be a function of depth and sediment entrainment. But what's the range that you would expect from one of those?
Well, it varies depending on what model you have. So some of the bigger ones with the bigger transducers, those are lower frequency and they have more power that they put into the water. They can go about 120 meters. And then the smallest model that we have, the 3000 megahertz, will go a couple meters. Yeah, so there's a huge range in between. The thing to understand though is, especially if you're doing an index, a velocity indexing, you don't need to go all the way across the channel. And you can index, an average over this much space to your mean velocity that you measure with an instantaneous measurement. I mean, it's something that people don't realize, that no, you don't have to measure this perfect, transect across the channel every time. You can pick what velocity and what parameters, velocity plus stage, velocity in this section or this section, averaged, whatever, that makes it the best fit in terms of the regression.
And you can play around with the ensembles, which ones you want to use.
Yeah, exactly.
To assess which of these gives me that best relation.
Exactly. Mm-hmm.
Thanks.
All right.